Yes, you're welcome, members, to this other lesson of ours. I'm Mr. Hyper taking you through. And today we are going to look at the applications of the distribution law, right? So this distribution law, which we introduced in the previous videos, has gotten its wide applications. And that is what we are going to be discussing today in this episode of our lesson. Amongst the applications of distribution law include solvent extraction, investigation of complex ions, distinguishing bromides and iodides. Also, it's applied in ion exchange and partition chromatography. So you're going to entirely look at these two first, then maybe we shall explain the rest later. When you talk about solvent extraction, right here, we are separating a component from a mixture by shaking it with the extraction solvent in which that component is more soluble, okay? So generally the process involves separating one component from the mixture, but shaking it with the extracting agent or with the extraction solvent in which that component, which can be a solute, is more soluble. Now, each layer, after shaking it, each layer is then corrected. We correct each layer, and the solute can be obtained by distilling of the extracting solvent. In other words, the extracting solvent, the choice of the extracting solvent should be such a way that it can easily be distilled off. Okay, so then basically when we say solvent extraction, okay, the moment we say solvent extraction, this one refers to the partial removal of a solute from a solvent or its aqueous solution by introducing another solvent immiscible with the first solvent, but in which the solute is more soluble. So the method generally involves removing a solute from a solvent or from its aqueous solution. So maybe you can have solute, maybe B, when it is in a certain solvent like water, I'm assuming. So to remove it, to remove this solute B from water, we have to introduce in another solvent, maybe ether. And that solvent you introduce, the solid should be more soluble in this solvent you are introducing, and this solvent should easily be distilled off. All right. So basically, that is what we call solvent extraction. You are removing a solid from a solvent or from its aqueous solution. How? By introducing a solvent which is immiscible with the first solvent. So if you bring in ether, ether should not be reacting with the water. In other words, it should be immiscible. They shouldn't mix to form a uniform solution. So don't have water, don't be having water here, and then you want to introduce in ethanol, because that ethanol introduced, okay, the ethanol introduced is miscible with this water, and therefore it cannot work as an extracting agent, or it cannot work as an extraction solvent. So we may not use it that way. So basically that is solvent extraction. And this process is normally applied in the purification of organic compounds which are present in aqueous solutions with ionic impurities. The substances are extracted with organic solvents such as like carbon tetrachloride, ether, or benzene. But we are going to realize that out of the extraction solvents used, ether is normally used, and we want to cover out the reasons as to why we prefer using ether. Okay, so this ether is preferred because of the following reasons. We prefer using ether simply because it is very volatile. Ether is volatile and therefore can easily be distilled off. Okay, that is one. Ether is volatile, so it can easily be distilled off. Two, This ether is a good organic solvent. It is a good organic solvent. 3, this ether is generally inert. And by it being inert, it means that it cannot react with the organic compounds. Another point is that it is immiscible. It is immiscible with water. It is immiscible with water. So these are the points that guide us to use ether as a good extracting solvent. And here, there is also another point. The extraction solvent has to be used in small amounts than using it at once, because the moment you use it in small portions, you'll be able to extract more solute, okay, by using several small portions of a solvent, okay? You use small amounts of solvent to extract a bigger amount of a solute. We are going to manifest this by calculations. So I'm really going to bring in the questions that are going to guide us, the calculations, and let's have our examples. Example 1, calculate the mass. Calculate the mass of an organic compound Q that can be extracted from 100 cubic centimeters of an aqueous solution containing 5.0 grams of Q by using part A 100 cubic centimeters of ether and part B 2 successive portions of 50 cubic centimeters of ether, Kd of Q between ether and water is 3. Right. They want us to calculate the mass of an organic compound Q that can be extracted from 100 of an aqueous solution containing 5 by using 100 cubic centimeters of ether. 2, by using 2 successive portions, right? Of course, as I told you, when you extract using 100 cubic centimeters, the value you get can be conclusively compared with the value that you get when you do using 2 portions of 50-50. We told you that when you use 50-50, here you're likely to get much more solute compared to someone who has done this one at once. Why? It's like when you prepare your food and you decide to eat it at once. When you eat all your food at once, you find that after eating your food, it has gotten done and you don't have more food. But someone who has eaten in portions, he has eaten a portion After some time, another portion. After sometimes another portion, that person will keep satisfied because he has eaten in portions. But for you who has eaten the whole 100 cubic centimeters at once, the moment you are to get hungry, you can get hungry and you report to police. But someone who has eaten in 2 successive portions, during lunch, 1 portion, during supper, another portion, this person is likely to still be satisfied by the end of the day. But you've eaten all of it for breakfast. You'll be telling me by midnight. Now, let's look at how best we can work out these things. Calculate the mass of an organic solvent, rather organic compound. I don't know why the word solvent is quite much in my mind. Okay. So now when we have to calculate the mass of an organic compound Q, we shall begin by letting the mass of Q extracted by 100 cubic centimeters of ether be X grams. So if we let this mass extracted by 100 cubic centimeters of ether to be X grams, it will mean that mass of Q remaining in the aqueous layer would be equaling to, remember in aqueous layer, it contained 5 grams. So if X goes to ether layer, what remains in the aqueous? 5 minus X grams. Very interesting. Now, I want you to remember that from the definition of KD, since I've given you KD, KD is given by the concentration of Q in which solvent? They say KD of Q between ether and water. Ether has come first. So you also here bring ether out of the concentration of Q in aqueous layer, which you normally take as water, right? But one may wonder, how are we getting the concentration of ether? How are we getting the concentration in aqueous layer? To get the concentration of Q in ether, we've gotten the mass that goes to ether layer, and we have the volume. So mass of a volume will give us the concentration. So concentration of Q in ether is going to give us X out of 100, whereas concentration of Q in aqueous layer or water layer, all right, is going to be given by 5 minus X out of 100, since the volume of the aqueous is also 100. Now we substitute in KD. All right, so it would imply that KD, which is 3, is going to be equal to concentration of Q in ether, which is X out of 100, divided by concentration of Q in aqueous, which is 5 minus X out of 100. So our 3 is X out of 100 times 100 out of 5 minus X. These ones will go, so that we have our 3 equaling to X out of 5 minus X. All right, so by cross multiplying, it will be 15 times, rather 3 times 5, which is 15, minus 3X is equals to X. When you bring X this side, it will be 15 is equaling to is equaling to 4X. Right, so here it can give us the value of X as 15 over 4, and you put on your calculator 15 over 4. All right, you get your 3.75. And the fact that you had said that let the mass of Q extracted by 100 cubic centimeters be X grams, meaning the value of X is the mass extracted by 100 cubic centimeters of ether. Let's go to the most interesting part B, right? Let's go to the most interesting part B of this question. Well, they want us to get the mass of organic compound Q that can be extracted when two successive portions of 50 cubic centimeters of ether are used. It means that we shall have the first portion of 50, we also have another portion of 50, making them two portions that sum up to 100, all right? Now, what we shall do, we shall let the mass of Q extracted by the first 50 cubic centimeters portion, by the first 50 cubic centimeters portion of ether maybe be X1 grams. It would mean that the mass of Q remaining in aqueous layer would be, initially we had 5, so it would be 5 minus X1 grams. But we know that Kd is equals to concentration of Q in ether over concentration of Q in water or aqueous layer. So our Kd does not change because it is a constant ratio. So it is 3 is equal to concentration of Q in ether. It is X1, but now out of 50 because we are using the first portion volume. Okay, so it is X1 over 50 divided by Q in water to be 5 minus X1 over the volume of water will keep the same, 100. So 3 is equal to X1 over 50 times the reciprocal, which will be 100 over 5 minus X1. This one will make 2X1 because this one will reduce by 1 and making this one 2. So we shall have 3 is equals to 2X1 out of 5 minus X1. When you do cross multiply, you get 15 minus 3X1 is equals to 2X1. And this one will come to 15 is equals to 5X1. So my X1 is giving me 3 grams. It means that in the first extraction, when we use the first 50 cubic centimeters portion, we get 3 grams. This is very, very, very interesting. We get 3 grams. Now, what about when we extract for another time? So that's what we want to see. That was the first time it has given us that. So after extraction with the first portion, okay, after extraction with the first portion, right? Mass of Q remaining in aqueous layer will be equaling to 5 minus X1, which is 5 minus 3. So we have 2 grams. 2 grams are remaining in the aqueous layer. So let's say let the mass of Q extracted using the second 50 cubic centimeters portion be x2 grams. Because we use the first 50 cubic centimeters, we got this. So when we use the second portion, the value of x2 that we shall get is one we shall take. So if it is x2, what about the mass remaining? Mass remaining in aqueous layer will be equaling to 2 minus x2 grams. So what does this imply? This would imply that Kd still is going to be equal to concentration of Q in ether, which would be x2. This would be x2 out of 50 divided by concentration in the aqueous, which would be 2 minus x2, but out of 100. But you know Kd, our Kd was 3, okay? I forgot to put it here. So it means that 3 is equal to x2 over 50 times the reciprocal, 100 over 2 minus x2. This one still will make it to x2, so it will be 3 is equals to 2x2 over 2 minus x2. When you do cross multiply, it will become 6 minus 3x2 is equals to 2x2. So 6 is equals to 5x2, and our x2 is going to be equal to 1.2. When you divide 6 by 5, 1.2 grams. Now, the first portion gave us 3. The second portion gave us 1.2. Total mass extracted by 2 portions will be equal to x1 plus x2, which will be equaling to 3 plus 1.2, and this is going to give us 4.2 grams. When you compare this answer with the other answer we got when someone used the whole 100 at once, which was 3.75, you're going to see that this one has extracted a much more solute or a much more substance compared to the one who used it at once. So this is how these questions be. Okay, this is how these questions be, and basically that is what we are having. Okay, so let's do another example. The more examples we do here, the more we shall understand this work. All right, so let's have an example 2. Calculate the percentage by mass of iodine, percentage by mass of iodine extracted from 100 cubic centimeters of water using 100 cubic centimeters of benzene. 2, using 2 successive portions. 2 successive portions of 50 cubic centimeters of benzene. So here, Kd of iodine between benzene and water is 5. Solution. For you, you should start working clearly knowing that the answer you'll get when you use 2 successive portions should be greater than when you use 1 portion at once. Should work knowing that. All right? So now, what we shall do, we shall have in our solution for part A, we shall let the percentage by mass of iodine, let the percentage by mass of iodine extracted by cubic centimeters of benzene be, maybe, now let's use Y %. Okay. It means that the percentage of iodine that will remain in the aqueous layer in aqueous layer will be equal to 100 minus Y %. Assuming that the total percent present initially was 100. Okay. Meaning here, it would mean that Kd will be equaling to the concentration of iodine. So they said between benzene and water, so we shall have benzene first, over the concentration of iodine in water. Kd is 5. Percentage of iodine in benzene will be Y. So the composition is going to be Y, but out of the volume. Actually, this was extracted by 100, not 50. Let's change this, 100 cubic centimeters of benzene. So Y out of 100 divided by 100 minus Y out of 100 cubic centimeters of water. So this one will give you 5 is equals to Y of 100 times 100 of 100 minus Y. When this one is cancelled, so I'll be left with 5 is equals to Y out of 100 minus y. So we shall have y is equals to cross multiply 500 minus 5y, right? And so we shall have 6y equaling 500. And this one will give us our y as 83.33%. And the fact that we had said that let the percentage by mass of iodine extracted by 100 cubic centimeters of benzene be y, and we've gotten y, then this one qualifies to be the answer for part A. Part B, what about when we use two different or two successive portions? What do we get? If we use two successive portions. What we shall do for two successive portions, we shall first look for the first portion, second portion, then we add them. And we expect the percent to be beyond 83.33. Let's see. Shall let percentage by mass of iodine extracted by the first 50 cubic centimeters portion of benzene be, let me call it X%. It implies that the mass of iodine remaining in aqueous layer is going to be 100 minus X. Let me call it X1, so that this one I call it minus X1. All right. So I apply my KD. My KD, which is 5, is going to be equal to concentration of iodine in benzene, which will be X1 over the first portion 50, divided by the concentration of iodine in aqueous, which will be 100 minus X1 out of aqueous volume, which was 100. Looking at this, you can really see that 5 is going to be equal to X1 over 50 times 100 over 100 minus X1. So this one gives us 2X1 on top over 100 minus X1. So when you cross multiply, you'll have 2X1 is equals to 500 minus 5X1. When you bring it this side, it will be 7X1 is equals to 500, and you'll get your X1 as 71.43% after having divided by 7. So after getting this first percent, we shall move to after doing the first extraction, okay, the mass of iodine, the percentage by mass of iodine remaining in the aqueous layer, okay? So after the first portion's extraction, percentage by mass of iodine remaining in aqueous layer will be equal to 100 minus X1, which is minus 71.43. And this is going to be equal to 28.57. So this is the mass that remains in the aqueous layer. So now we go on and say, let the percentage the mass of iodine extracted by the second 50 cubic centimeters of benzene be x2%. It means that the percentage by mass remaining, okay, percentage by mass remaining in the aqueous, layer will be 100, no, not 100, because the mass now we have is this. So we shall have 28.57 minus x2%. All right. Now we are applying the K distill, so it will be 5 is equals to concentration of iodine in benzene, so it will be x2 out of the second volume divided by percentage or the concentration of iodine in aqueous, which will be 28.57 minus x2 out of 100. So 5 is going to be x2 over 50 times 100 over 28.57 minus x2. All right, so looking at this, we shall have 5 is equals to 2x2 divided by 28.57 minus x2. So looking at this, summarizing all this, it will be 2x2. We're going to be going to 5 into 28.57 minus x2. All right. And this one will give us our x2. After working on it, it will give you 20.42%. The first extraction gave us this. The second extraction has given us this. So if we need the total mass of iodine extracted by the two portions, will be equaling to x1 plus x2, which is going to be equal to 71.43 plus 20.42, and this is going to give us 91.84%. That is what we are having. All right. So that way you would be very, very, very safe with the value. Now, example 3. Example 3, 50 cubic centimeters of a solution containing 0.966 grams of iodine in tetrachloromethane cubic centimeters of a solution containing 0.966 grams of iodine tetrachloromethane was shaken with 50 cubic centimeters of water. 1. Calculate the amount of iodine calculate the amount of iodine that remained in the tetrachloromethane layer. In tetrachloromethane layer, KD between tetrachloromethane layer and water is equals to 85, sorry, 0.25. That is the KD. 2, explain how you answer in Roman 1 would be affected if the iodine solution in tetrachloromethane was shaken with the aqueous potassium iodide, let me abbreviate as Ki, instead of water. Instead of water, how would it be affected? Wow. 50 cubic centimeters of a solution containing 0.966 grams of iodine in tetrachloromethane was shaken with 50 cubic centimeters of water. But the amount of iodine that remained in the tetrachloromethane layer or the organic layer. Okay, now let's let the mass, that is Roman 1, let's let the mass of iodine extracted by, since they gave me the mass of iodine in tetrachloromethane, so I don't know the mass extracted by 50 cubic centimeters of water. So I'm letting the mass of iodine extracted by 50 cubic centimeters of water to be X grams, all right? Implying that the mass of iodine remaining in tetrachloromethane will be equaling to 0.966 minus X gram. It is very interesting. Here you know the mass in tetrachloromethane. And you've said that the mass of iodine extracted by 50 cubic centimeters of water be X, because you don't know the one of water. So if I need the mass, if X goes to aqueous layer, then what remains in the organic layer? It will be what you have minus what had gone to the aqueous layer. So from KD, the fact that I've said the KD of iodine, it is KD of iodine between KD of iodine between tetrachloromethane and water. So it will be KD is equals to Concentration of iodine in tetrachloromethane over concentration of iodine in water. So KD is 82.25 is equals to concentration of iodine in tetrachloromethane 0.966 minus X over the volume of tetrachloromethane 50 centimeters of solution containing that of iodine tetrachloromethane. So we have 50 divided by, for water, it will be X, and we are given water volume as 50. So this one can easily give me the answer, and the 50s will cancel after the cross multiplying. So we shall have 82. Sorry, I'm using a wrong KD, which is 85.25. 85.25 is equals to 0.966 minus X out of X. Right, so this one, when you cross multiply, it is 85.25 is equals to actually X is equal to 0.966 minus X. So when you bring it here, it will be 86.25X is equals to 0.966. So when you divide, you get your value of X as 0.0112 grams. After getting this, this is the amount that goes to water or the aqueous layer. So the amount of iodine, they want us to calculate the amount of iodine that remained in tetrachloromethane, which is this. So we shall substitute for the value of X. So amount of iodine remaining in the organic layer or in tetrachloromethane layer is going to be 0.966 minus 0.0112. And this is going to be 0.9548 grams. That is the mass that remains in the tetrachloromethane layer. Very interesting question. Part 2 is saying, how would your answer in 1 be affected if iodine solution in tetrachloromethane layer was shaken with the aqueous potassium iodide instead of water? You're having this answer, 0.9548. Will the answer reduce or it will increase? My answer is it would reduce. Why? So I will first say, remember we are replacing water with the potassium iodide. So my answer will first be the mass of iodine remaining in tetrachloromethane layer would reduce. Why? The iodide ions in the potassium iodide solution combine with the iodine form a soluble complex. That is what we should first know. Okay. In potassium iodide, there are iodide ions. So the iodide ions present in the potassium iodide solution combine with iodine to form a soluble complex. Which complex is that? Triodide ions. So we have that plus the iodide ions. We shall form a triodide ions. This is a complex that we form. Now, this one would mean that the concentration of iodine in aqueous layer has reduced because it's being used to form a complex. Okay, so the concentration of iodine in aqueous layer reduces, right? So this the formation of a complex reduces the concentration of iodine in the aqueous layer. And for equilibrium to be established, okay, more iodine has to move from the organic layer to the aqueous layer. That's why the mass of iodine remaining in the tetrachloromethane would reduce. Why? The iodide ions present in the potassium iodide combine with iodine to form a soluble complex. The formation of a soluble complex reduces the concentration of iodine in aqueous layer. Now, for the equilibrium to be established, more iodine moves from the organic layer to the aqueous layer. And as it moves from the organic layer or from the tetrachloromethane layer, it means that the mass of iodine in the tetrachloromethane is reducing. So that is simply what causes the facts. Okay. I'm doing this example too. Also, I'm going to do another example. This one, I'm going not to complete it, but instead I'll give you a tip and you complete it. A solid Q is 3 times as soluble is 3 times as soluble in solvent X okay, as soluble in solvent X as in solvent Y. Okay. Q has the same relative molecular mass in both solvents. Calculate the mass of Q that would be extracted from a solution from a solution of 4 grams of Q and 12 cubic centimeters of Y with 12 cubic centimeters of X, 2 6 cubic centimeters successive portions of X. Solid Q is 3 times as soluble in X as in Y. This statement here gives us the value of a KD, So that is, I want to help you get KD and then you move it. Now, it would imply that if they said solid Q is 3 times as soluble in X, it means that it is more soluble in X than in Y. Actually, it is more soluble in X 3 times than in Y, meaning the concentration of Q in X is 3 times the concentration of Q in Y. Meaning if you divide by concentration of Q both sides, we are going to have that Q, concentration of Q in X out of concentration of Q in Y is equals to 3. And then you move on. So it gives us the KD, but you need to know what to put up and what to put down by following the statement. A solid Q is 3 times as soluble in X as in solvent Y. So from there you can push it. Another logical question would be, which would be like our number 5, would be when 1 liter of an aqueous solution containing 25.0 grams of solid X was shaken with 500 cubic centimeters of ethoxyethane (9.7 grams of X) was extracted in the ethoxyethane layer. Calculate the partition coefficient of X between ethoxyethane and water. And B, the solution in B was shaken with 2 successive (250 cubic centimeters) portions of ethoxyethane calculate the total mass extracted, and C, comment on the result in B. Still, this is very easy because you need first now to get KD if it is not given. They say that when 1 liter of an aqueous solution, 1 liter of an aqueous solution, what does it mean? It means that an aqueous solution has 1,000 cubic centimeters. Containing 25.0 grams of solute X was shaken, 9.7 was found in the ethoxyethane layer. So if 9.7 was found in the ethoxyethane layer, then we can get the mass remaining in water, because the aqueous solution had this. Now, after extraction, 9.7 was extracted in the ethoxyethane layer, meaning we can get the mass in water. So I'm going to do part A by saying that we know that KD is equals to the concentration of X, since they want when 1 liter of an aqueous solution was shaken in this, they want you to calculate the partition coefficient of X between ethoxyethane and water. Ethoxyethane has come first, so we shall say ethoxyethane, or one can say organic layer, which is the ethoxyethane, over the concentration of X in the aqueous layer, which is water, right? So if 9.7 was extracted in the ethoxyethane layer, okay, then mass remaining in water would be equaling to 25 initially minus the one that went to ethoxyethane layer. So this one would give us 15.3 grams. So to get KD, shall say that KD is equals to concentration of X in organic layer. The concentration of X in organic layer would be 9.7 out of the volume of organic layer, which is 500, divided by the mass that remains in the aqueous layer, that is 15.3, divided by the total volume of aqueous layer, which is 1,000. So it's going to be 9.7 divided by 500 times 1,000 out of 15.3. And this one is going to give us 1.27 as our KD. So if the KD is 1.7, you can do part B. Okay, you can do part B, because now they're saying that the solution in B, okay, now it is in A. The solution in A was shaken with 2 successive 250 cubic centimeters portions of ethoxyethane. Remember, you initially had the 25 grams of aqueous. So it means that if X goes to 25, then you can get the mass that remains in aqueous. No, sorry. If I let, you'll do it, but here you'll have to let the mass extracted by first 250 cubic centimeters portion, maybe BY or Y1. Then the mass that remains in the aqueous will be 25 minus Y. Then you first carry out that, then you do it twice and you see After using 500 at once, they got 9.7. So what about when you use 250, 250? What will you get? If the answer is not above this, no, you have made a mistake. Okay, so it has to be beyond this. Then for the comment, they just want you to comment. Comment. You'll say the mass extracted by 250 cubic centimeters portion is greater than the mass extracted by using 500 portions once or at once. So the word successive also can be taken. So that is the first lesson of our calculations, and that is the first application of solvent extraction. Now we are going to look at the second application. Okay, we are going to look at the second application, which is the investigation of complex iron. We'll meet in another video or in another lesson, members. I wish you all the best and God bless you.